Let's use what we figured out about sine charts and where a function is increasing and decreasing to get information about local minimums and local maximums for a function. So first let's build a sine chart for the derivative of this function, this polynomial here. So let's calculate the derivative first of all. It's 12x squared plus 6x minus 6. Let's factor out a 6. So 2x squared plus x minus 1. And remember, to make a sine chart, we need to know where is this function 0. Well, where is it undefined, and where is it 0? It's defined everywhere, so now we need to know where it's 0. To know where it's 0, we can factor this one. It's 2x minus 1 times x plus 1. So is that right? 2x? Yes, that's right. So this one gives us x equals a half, and this one gives us x equals minus 1. Okay, so now we can start building our sine chart. We need to put these x values on our sine chart, so minus 1 and plus a half. This breaks the number line up into 3 pieces, these 3 pieces. And on each piece we can plug in sort of a test value to see whether this derivative is positive or negative for the number that we chose. So let's try, how about minus 2? So f prime of minus 2 is, let's see, 12 times minus 2 squared is 4, plus 6 times minus 2, so that's minus 12 minus 6. So this is definitely going to be positive. I don't even need to know what this is exactly. I just need to know if it's positive or negative. And this part's so big that it's definitely going to win. So this is positive. Okay, so plus over here. Remember, so on this interval, f prime is positive. So our sine chart is pluses here. Okay. All right, now let's pick a test value between minus 1 and a half. Might as well choose 0. That's a nice easy one to do. So f prime of 0, that's minus 6. That's definitely less than 0. So on this interval from minus 1 to a half, f prime is less than 0. So negatives. F prime is negative on this interval. And now let's do, how about 1? F prime of 1 is, looks like it's going to be 12 plus 6 is 18 minus 6, 12. And that's positive. So on this interval, f prime is positive again, like this. Okay. So we know that f itself is increasing on this interval, decreasing on this interval, and increasing on this interval. Well, at minus 1 and at 1/2, remember our goal here is to figure things out about local minimums and local maximums. Well, this row of our sine chart here gives us essentially an extremely rough graph, or rough sketch of the graph of f. Over here the graph is increasing. At x equals minus 1, right? Remember, we put x equals minus 1 on this sine chart because the derivative here is exactly 0. So that means we have a critical number. We have a horizontal tangent line like this. Well, if the function is increasing and then it flattens out and then it decreases, this clearly has to be a local max. And the opposite happens at 1/2, right? At x equals 1/2, the derivative is 0. So we have a horizontal tangent line. But if the graph is decreasing and then goes horizontal and then increases, this has to be a local minimum. So you can see just by looking at the pattern of the signs of the derivatives, we can tell if these critical numbers are local mins or local maxes. So if the derivative goes from positive to 0 to negative, that's a local maximum. If it goes from negative to 0 to positive, that's a local minimum. Well, what would it look like if so this is a made-up example, no longer working with that previous formula. What would it look like if the derivative went from negative to 0 to negative again? Well, then we would have the original function would be decreasing, and then it would have a horizontal tangent line, and then it would be decreasing some more. Well, again, this essentially is an extremely rough graph of f, or an extremely rough sketch of the graph of f, and this critical number here, this place where there's a horizontal tangent line, it isn't a local maximum because the graph must be higher over there, but it's not a local minimum because it must be higher over there. So in this situation, if the derivative goes negative 0, negative, this critical number is not a local min or a max. And the same kind of thing happens if we have the derivative going from positive to 0 and then back to positive. Right? The original function would be increasing, and then it would have a horizontal tangent line, and then it would keep increasing. In this situation, at this critical value, it's not a local maximum because the graph is higher to the right, and it's not a local minimum because the graph is higher to the left. So again, in this situation, it's not a local minimum or a maximum. So what we seem to be seeing here is that if we have a critical number, a place where the derivative is 0, or if the derivative doesn't exist, it turns out, and the derivative switches from positive to negative, it's a local max. If it switches from negative to positive, it's a local min. And if it doesn't change at all, if the derivative stays negative or stays positive, then that critical number is not a local minimum or a maximum. This is actually called the first derivative test. So if you have a function that's defined on some interval around a, and the derivative changes from negative to positive at a, then you're at a local minimum. If the derivative changes from positive to negative at a, then you're at a local maximum. And if the sign of the derivative doesn't change sign at that x value, then it's not a local minimum or a local maximum.